right, we're going to do solutions to some of the problems I suggested you practice that we didn't get in the review today. This first set of three are limits from 1.9. So this was kind of some of the earlier work. So as we were working backwards, we didn't get to review these at all. All of these limits you would use algebraically, meaning first I'm going to use the idea that if a function is continuous, so we'll just briefly recall that over here. So recall, if a function is continuous, then that means not only does the limit exist and is the function defined, but those values are the same. So the limit as x approaches a of f of x has to equal f of a. How does this help us? Well, if I can have a function that's continuous or rewrite it algebraically so it seems continuous at the point I want to find the limit, then to find the limit, I just find the value of the function. So that's our strategy. If we look at number 11, we notice that if I were to plug 3 into x as is, I would get 0 over 0. 0 over 0 is an indeterminate form. It has no meaning, so that's not going to work. So my strategy is going to be to do some algebra to make that limit look like something different that I can just evaluate at 3. So when I have polynomials like in 11 and in 12, my strategy first would be to factor. So the limit of this function is going to be equal to the limit. Notice I'm still writing limit because I haven't evaluated it yet. The numerator is going to factor as a difference of two squares, so x minus 3 times x plus 3. The denominator factors to be x plus 4 times x minus 3. Now it becomes apparent that I can cancel out the x minus 3's. So this will actually look like a function that has a hole at 3, right? Remember, if the numerator and denominator are both 0, then there's a hole as opposed to an asymptote. So there will be a hole at 3, but the function will still be approaching this value. Now what's left, I can evaluate at 3. So I'm going to drop the word limit because I'm actually evaluating it. When I substitute 3 in now, I get 6 in the numerator and 7 in the denominator. So even though there will be a hole in the function, the limit as x approaches 3 will be 6/7. Number 12 is going to be very much the same way. I'll leave you guys to try that one on your own. And the answer to number 12 should be 3/4. So go ahead and try that on your own and make sure you get 3/4. Number 13 is a little bit different because the algebra works out different. We are going to expand instead of factor, but it's going to be the same idea. If I plug in 0 as is, I get 0 over 0, which I can't tell you what is happening. So my next strategy is to do some algebra to simplify the expression so that maybe I can evaluate it. So in this case, I'm going to expand what's squared, and hopefully things will cancel out for me. We also now recognize this kind of a limit with the h in the bottom is leading us towards what we're going to need to do to find derivatives. So in this case, when I expand the top, I'm going to get 9 plus 6h plus h squared, and I still have the minus 9, all divided by h. So combining like terms, 9 minus 9 would be 0, so they essentially cancel out. And I'm going to factor the h out here just to make it a little bit easier to see what I can and can't cancel, and so I don't make any careless mistakes. By factoring out the h, now everything's connected by multiplication. So when I have common factors connected by multiplication, I can reduce them. So I'm left with the limit as h approaches 0 of 6 plus h. So I have the limit as h approaches 0 of 6 plus h. So I have now succeeded in simplifying my original function to something much simpler that is continuous at 0. So now I'm going to drop the limit because I'm evaluating it. When I plug in 0 for h, I get 6. So the limit of this function is going to be equal to 6. The other problem that we looked at was the one of kind of analyzing everything we've been doing so far. This is number 40 from section 2.5. There is a typo. There's been a typo on the online. This should be as x approaches negative infinity. It doesn't really make sense to have two different limits towards positive infinity. So that one is x approaches negative infinity. So this basically puts together everything we've been doing, right? We have the idea of limits to infinity, the derivative, the second derivative, and we want to put all of this together to sketch a possible function f that would have all of these properties. So what I like to first do is kind of a visual organizer to see what's going on. So I would draw a number line and kind of write down what does it mean for my function f when the first derivative is positive and negative and the second derivative is positive and negative. So I'm kind of setting up a little table and I'm lining it up on a number line so I can sort of map out what f should be doing. And then I'll try and put it together with the limits. So the first one tells me, so I'm kind of looking at these numbers. It looks like I have something happening at -6, then at -3, then at -2. The next number they give me is 0, and then +3 and +6. This doesn't look really to scale there, but I've kind of marked the interesting points in order so I can mark out my number line. So looking at the first derivative is positive between -2 and +2. Oh, I forgot my +2 there. So between -2 and +2, the first derivative, let me move these down here so they're not getting in the way of my numbers. So I'll write f prime here, f double prime here. So between -2 and +2, the first derivative is positive. That means that my function f should be increasing. Right now, I'm just going to draw f as linear pieces because I'm just thinking about increasing, decreasing when I'm talking about the first derivative. And then we'll add the concavity when we look at what's happening with the second derivative. It tells me now that the first derivative is negative in between -6 and -2, and then in between 2 and 6 as well. The first derivative is negative, which means in between -6 and -2, my function is decreasing. And in between 2 and 6, my function is decreasing as well. So that tells me when my function's increasing and decreasing. Now I can add in the concavity. So it tells me that the second derivative is positive in between -3 and 0. So in between -3 and 0, my function should be concave up. And then furthermore, in between 3 and 6, the second derivative is positive as well, which means in between 3 and 6, this function again is concave up. But be really careful, it still has to stay decreasing. So that piece in between 3 and 6 is going to be concave up and decreasing, looking a little bit like an exponential decay function. Now in between -6 and -3, my second derivative is negative. So that means here, my function is concave down. So it's going to be concave down until we get to -3, and then it's going to turn to be concave up. And then in between 0 and 3, again, my second derivative is negative, which means, again, my function in between 0 and 3 should be concave down. And in between, we had -6 to -3. I feel like I'm missing something. From -3 to 0. Oh, and 0 to 3 is also negative. Sorry, so all the way at 0, so starting here, we have our concave down. So our function looks a little bit something like that. We've got something a little bit interesting happening here at -3, right? Because from -6 until -3, my function's concave down, and now it's going to turn to concave up. But in between -6 all the way to -2, my function has to continue to be decreasing. Now let's kind of throw in these limits. Limits to infinity are going to be horizontal asymptotes. So that means if I go really, really far to the left, this graph is going to kind of flatten out at y equals 2. And when I go really, really far to the right, this graph should flatten out at y equals 3. So kind of following it all the way from the left to the right. As I'm coming in from the left, I should start at a height of 2. And then as I get to -6, my function is going to start decreasing all the way until I get to -2. Then it's going to increase until I get to +2. And then it's going to decrease again until I get to 6. And then it's going to flatten out to be y equals 3. With the concavity, as it comes in from the left, from -6 to -3, it's going to be concave down. So it's going to come in flat, concave down. And then at -3, it's going to start being concave up all the way until 0. And then at 0, it's going to switch to be concave down again. It's kind of, that's between these two turning points. And then between, when it gets to 3, it switches to be concave up. So let's kind of put all of that together. Kind of have a rough picture of our graph right there. Let me move this one. Oops. All right. So we have some room. So kind of putting everything together. And let's see if I can make this look prettier with graph paper. It's pretty thin graph paper. All right, that looks a little bit better for me. So we can't see any more of my markings, but I have them. Hopefully maybe you took some notes. If not, you might want to kind of pause, go back, draw the number line for yourself and try and put the graph together on your own and then come back and check it. But I'm going to, draw my grid here, hopefully. Maybe the third time's a charm. And this would be my x-axis. I don't know why I squiggled at the end there. Try that one more time. And then we have up here at 1, here's where y is equal to 2. So that's where my graph is coming in at the left. It's going to have a horizontal asymptote at 2. And then here at y equals 3, that's where my graph is approaching on the far right, because that was our limits. And then the points that we said were important, we had -6. So here's -1, 2, 3, 4, 5, -6. And then at -3, so 1, 2. And at -2, here's 0, of course. And then +2, +3, +6. So we said that again. Let's kind of review our shape. Our graph is going to come in from 2. And then when it hits -6, it's going to be concave down and decreasing, right? So as we come in from 2 and I hit the point where x is -6, my function should start being concave down and decreasing until we get to 0. At 0, it's going to start to be concave up, right? And at -2 is when it starts to be increasing. So I'm coming in as I hit -6. It's going to be concave down and decreasing, and it's going to, it will continue that pattern of being concave down and decreasing until we get to -3. At -3, it's going to start to be concave up, but it's going to start, let me start again here. Concave down, decreasing, and it's going to keep decreasing all the way until we get to -2. So I'm going to keep having it decrease all the way until we get to -2. At -3, it kind of starts turning around because that's where it starts becoming concave up. Now at -2, it's going to increase all the way until +2. So it's concave up, and at 0, it kind of starts turning around to be concave down at +2. I want to make sure that I get above 3 here because I know it's going to have to decrease back to 3. So it's going to keep going. It's going to turn around. It's going to keep going up, up, up. And now it's going to start still going up, but be concave down. Whoops, that did not work out. So now it's increasing, and now it starts to be concave down, and it's going to turn around at 2. All right, and then when x is equal to 2, in between +2 and +6, my first derivative is negative, so my function is going to start decreasing. So it decreases all the way from 2 to 6, but in between 3 and 6, it's going to turn around and be concave up. So what that looks like is in between 2 and 6, it's going to keep decreasing. So it's here between 2 to 6. It's going to, let me make this increase a little bit higher. So it's going to keep going up, 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 and then it's going to start turning around at 2. From 2 to 6, it's going to decrease, and at 3, it's going to start to be concave up. And then it's just going to approach 3. So that is how you would do it.